Welcome back to the world of electricity. This presentation is about voltage, the force that pushes electric current. As was previously mentioned, we need more than just a continuous path called a circuit before a continuous flow of electrons will occur. We also need some means to push these electrons around the circuit. Just like marbles in a tube, or water in a pipe, it takes some kind of influencing force to initiate the flow. With electrons, this force is the same force that is at work in static electricity, the force produced by an imbalance of electric charge. If we take the examples of wax and wool which have been rubbed together, we find that the surplus of electrons in the wax, negative charge, and the deficit of electrons in the wool, positive charge, creates an imbalance of charge between them. This imbalance manifests itself as an attractive force between two objects. If a conductive wire is placed between the charged wax and wool, electrons will flow through it as some of the excess electrons in the wax rush through the wire to get back to the wool, filling the deficiency of electrons there. The imbalance of electrons between the atoms in the wax and the atoms in the wool creates a force between the two materials. With no path for electrons to flow from the wax to the wool, all this force can do is attract the two objects together. However, now that a conductor bridges the insulating gap, the force will provoke electrons to flow in a uniform direction through the wire, if only momentarily, until the charge in that area neutralizes and the force between the wax and the wool diminishes. The electric charge formed between these two materials by rubbing them together serves to store a certain amount of energy. This energy is not unlike the energy stored in a high reservoir of water that has been pumped from a lower level pond. The influence of gravity on the water in a reservoir creates a force that attempts to move the water down to the lower levels again. If a suitable pipe is run from the reservoir back to the ground or the pond, water will flow under the influence of gravity down from the reservoir through the pipe, much as it does in this water tower. It takes energy to pump that water from the low-level pond to the high-level reservoir, and the movement of water through the piping back down to its original level constitutes a releasing of energy stored from the previous pumping. If the water is pumped to an even higher level, it will take even more energy to do so. Thus, more energy will be stored and more energy released if the water is allowed to flow back through the pipe down to the bottom again. Electrons are not much different. If we rub wax and wool together, we pump electrons away from their normal levels, creating a condition where a force exists between the wax and the wool, as the electrons seek to re-establish their former positions and balance within their respective atoms. The force attracting the electrons back to their original positions around the positive nuclei of their atoms is analogous to the force of gravity that it exerts on water in a reservoir, trying to draw it down to its former level. Just as the pumping of water to a higher level results in energy being stored, pumping electrons to create an electric charge imbalance results in a certain amount of energy being stored in that imbalance. And just as providing a way for water to flow back down from the heights of a reservoir results in the release of that stored energy, providing a way for electrons to flow back to their original levels results in a release of that stored energy, such as in this electric light circuit. When the electrons are poised in a static condition, just like the water sitting still high in a reservoir, the energy stored here is called potential energy, because it has the possibility or potential of release that has not been fully realized yet. When you scuff your rubber-soled shoes against a carpet on a dry day, you create an imbalance of electric charge between yourself and the carpet. The action of scuffing your feet stores energy in the form of an imbalance of electrons forced from their original locations. This charge, static electricity, is stationary, and you won't realize the energy is being absorbed at all. However, once you place your hand against a metal doorknob with lots of electron mobility to neutralize your electric charge, that stored energy will be released in the form of a sudden flow of electrons through your hand, and you will perceive it as an electric shock with a spark. This potential energy can be stored in a form of electric charge imbalance and is capable of provoking electrons to flow through a conductor. It can be expressed as a term called voltage, which technically is a measure of potential energy per unit of charge of electrons, or something a physicist would call specific potential energy. Defined in the context of static electricity, voltage is the measure of work required to move a unit of charge from one location to another against the force which tries to keep the electric charges balanced. In the context of electrical power sources, voltage is the amount of potential energy available, work to be done per unit of charge, to move the electrons through the conductor. Because voltage is an expression of potential energy, representing the possibility or potential for energy release as the electrons move from one level to another, it is always referenced between 2 points. Consider the water reservoir analogy. Because of the difference in the height of the drop, there's potential for much more energy to be released from the reservoir through the piping to location 2 than to location 1. The principle can be intuitively understood in dropping a rock, which results in a more violent impact. A rock drop from a height of 1 foot, or the same rock drop from a height of 1 mile. Obviously, the drop of the greater height results in greater energy released, a more violent impact. We cannot assess the amount of stored energy in a water reservoir by measuring the volume of water any more than we can predict the severity of a rock's impact simply from knowing the weight of the rock. In both cases, we must also consider how far these masses will drop from their initial height. The amount of energy released by allowing a mass to drop is relative to the distance between its starting and ending points. Likewise, the potential energy available for moving electrons from one point to another is relative to those 2 points. Therefore, voltage is always expressed as a quantity between 2 points. Interestingly enough, the analogy of a mass potentially dropping from one height to another is such an apt model that voltage between 2 points is sometimes called a voltage drop. This is the end of part 1. The second half will continue our discussion of voltage.